Hello everyone, good afternoon, and this is Zhengyu Zhang. So, the talk today my talk is on my paper, which is set by ICIP 2022, and the name is Deep Bright Lightfield Image Quality Assessment by joining angular and spatial information. Here is the outline of my talk. And first, I will introduce the Lightfield image quality assessment, and then followed by the motivation of our work. And after that, I will introduce our proposed metric named Deep Brief, including overall framework and spatial angular path generation and 2G CL model. And finally, after showing the experimental results, the conclusion will be drawn. And I will start with the introduction. Well, Lightfield image is a novel image format with great potential to provide a powerful immersive experience. And Lightfield image can be captured by a Lightfield camera or camera array, and which results in an array of 2D images. And this kind of representation of Lightfield image is named sub-aperture image, as shown on the right side of the slide. And we can see that each sub-aperture views contains very similar, but actually different contents. And Lightfield image contains spatial information like 2D images and contains the angular information between different views. And in the Lightfield image processing chain, many kinds of the procedure will be introduced into Lightfield image. And as a result, different kinds of the distortion will be introduced in Lightfield image, which affect its quality. And that is our visual experience. And so it is very necessary to measure these kinds of the distortion in Lightfield image. And as we mentioned before, as Lightfield image contains not only spatial and angular information, so Lightfield image or the distortion of Lightfield image also can be divided into spatial and angular distortions. Then I will introduce the motivation of my work. Now, actually, most existing non-reference Lightfield image quality assessment metrics still use multiply handcraft features and followed by support vector regression to obtain the Lightfield image quality. And in fact, these kinds of metrics often result in unsatisfactory performance and high time complexity. And here, no reference means that we measure the quality of the distorted Lightfield image without any reference and undistorted information. Well, alternatively, we consider to extract the discriminative features by convolutional neural network to obtain the Lightfield image quality. But in practice, two challenges are faced when adopting CNNs for quality assessment. First, there is no enough Lightfield image data for training a CL model. And generally, now most of the Lightfield image data set only contains hundreds of distorted Lightfield image, and yes, are quality labeled. So there is no enough data for training a well-performing model. And second, there is no CL model superphysically decided for Lightfield image quality assessment. So, to address these two challenges, we propose a novel metric named Deep Brief. Here, the full name of the proposed metric is Deep Bright Lightfield image quality assessment, and the overall framework shown. It consists of two main components. That is spatial angular path generation model and 2-string CL model. First of all, firstly, when we input the aperture image array of Lightfield image, we first use the spatial angular patch generation model to extract a large number of the spatial angular patches to enlarge the training data set. And then for each patch, we use a two-string CL model to extract its potential features and further predict its patch quality. And after generate all the patch quality, all the patch quality is averaged into the overall Lightfield image quality. And here, these two main components will be detailed in the following. So, this is the diagram of the spatial angular patch generation model. Let's start with the left top side. And here, inputs are 9 by 9 so aperture image array of Lightfield image. We first only use the Y components of the central 5 by 5 views. This procedure is just used to reduce the computational complexity. And then we use a sliding window to crop the same position of different views. And after generate all the blocks, and all the blocks are created into one patch. This patch is named the aperture patch. And then, as the sliding window moving, or after sliding over all the position of all the views, and we can get a large number of the aperture patches. And finally, as shown on the right side, all the aperture patches are converted into the spatial angular patch by combining all pixels at the same position of different views. That is in this model, actually we just generate a large number of the patches which contains both angular and spatial information. And then, since the spatial angular pattern contains two kinds of information, and we propose to extract these two kinds of information in different ways. And for the angular information, or at the top side, you can see that since the angular information is recorded in every in adjacent pixels, so we propose to use CNN kernels with one deletion. That is a very classic CNN to extract the angular features. And for the spatial information, as the spatial information is recorded in every 5 pixels, here are 5. Why 5 pixels? Because here we only use the central 5 by 5 views to generate the patch. So the spatial information is recorded in every 5 pixels. So here we propose to use CNN kernels with 5 deletion to extract the spatial features. And based on which two-string CN model is decided. And at the end of this two-string, the angular and spatial feature maps are concatenated and followed by 2 fully connected layers to predict the patch quality. And finally, all the patch quality are averaged to generate the overall Lightfield image quality. And then I'd like to show some experiments of our paper. First of all, I would like to introduce the experimental setting. To validate our proposed metric, we conduct our experiments on Win5 Lightfield dataset based on K-force cost validation. And here, K subtract 2 force are used for training, and the remaining 2 force are used for testing. And note that here, each force only contains the distorted version of only one thing. That is to ensure that all the floors, the contents of each floor completely speed, yes. And since there are 10 reference things in Wing5 Lightfield dataset, so if we use the way to provide k subject 2 force for training and remaining 2 force for testing, actually we have a total of 45 possible floor combinations in total. So here we need to conduct the experiments for 45 times to ensure that all the combinations are considered to make a fair comparison. And finally, we report the average result. And 3 evaluation criteria are used to report the performance. That is PLCC, SROCC, and RMSE, and they focus on different aspects. Here is the experimental results. Table 1 shows the overall performance comparison of our proposed metric and the state of the qualitative assessment metrics. And we can see that our proposed metric on the bottom side achieves the best performance compared with the state of the metrics. And all these metrics are the performance of all these metrics are reported in the same K-force cost validation. And table 2 shows the evaluation study of different combination of strings. And we can see that using 2 strings, that is both angular and spatial string, can perform better than using a single string. And finally, I would like to make some conclusions. First, we can see that the CM features show discriminative ability for quality assessment of Lightfield image. And second, in the evaluation study, we can see that the quality degradation of Lightfield image can be reflected in both angular and spatial information. And finally, in this paper, we propose a novel metric named for quality Lightfield image quality assessment. That's all. Thanks for listening, and questions are welcome.
I have a first question. About the conclusion. Now, can you start the conclusion, please? Or you can stay here if you want. So you said that the angular and the spatial aspect impact the metric that you generate. So here with the evaluation study, you show that, is there one that is more important than the other? And is for some images, is one more important? And can you explain for one image where you get the quality, you measure the quality, can you, I don't know, have a kind of explainability telling you whether the information was bad or the quality was bad on the angular or on the spatial side of it?
You mean table 2, the evaluation study? That is just to, you can see that the proposed model contains 2 strings.
Yeah.
And this evaluation study shows that using the 2 strings and concat these 2 features can perform better than only use 1 string.
But you don't try to go the other way around and to say, okay, here I have an image, here is its score. And why is the score not good? I don't know. Why is the quality of this image bad? Is it because of the angular stream or is it because of the spatial stream? Can you explain like why the quality of the image was not good?
You mean that how to say why the performance is better for this feature response to the score?
What is the contribution, I would say, of the 2 streams? I mean, basically, you show that having the 2 streams is interesting, but it is for all images. Or for some images, would it be interesting to only have the spatial stream, or for other images only to have the angular stream, or do they always contribute equally to the metric that you produce?
I think this these 2 streams only suitable for the Lightfield image. That is the as I'm working.
Another question. You were assessing the quality. In your dataset, you got quality image, I don't know to call them, and then deformed image. Would the deformation were created artificially, or are they just?
We get the quality of the distorted image by subjective experiments by observer.
Okay, by the observer. So it's not like fake distortion. It's like the picture and you assess it. Right. Okay.
Yes, you didn't say which distortions were created on the images. Which type of distortions?
Actually, in this paper, of course, I have done this experiment, but in this paper, I don't show the details of the detail which distortion is better or which distortion is worse. Yes.
No, I mean, do you have like compression distortions or blur or other types? No.
Yeah, other types you mean? Other types?
No. Which distortions are present in this database?
Or here I don't show, but or actually there are 22 distortion types in this data set, and containing HEVC and two angular distortion and two learning based I can show you. Try that. And here the last two is the deep learning based matching to generate a distorted version.
So all those distortions are synthetic. So you have the same image with and without distortion?
Yeah, we have a reference image and then we use these kinds of distortion to generate a distorted.
Yeah. So how do you assess that your system is not detecting your distortion, but really assessing the quality?
Sorry.
We could say that your neural network in some way is detecting both specific distortion. And what is the difference between both specific distortion and quality?
Maybe I don't get your point.
But the idea is that you got a finite number of different distortion,
yes,
which are artificial. How do you detect that this is that your neural network assesses the quality and not the neural network just detects that a certain distortion has been applied? Something much more, quality is much more general. That a few, are you able to detect a distortion by learning on the other distortion? Like it could be the verification test to verify that you are able to detect the distortion even if you haven't trained on it.
You mean that you just wonder if my network can detect which kind of the distortion it is?
Maybe not even which kind, but just detect distortions that he hasn't been trained on to really detect quality and not just detect a selection of distortion.
Maybe I'm not sure here.
Did you try to train on some maybe compression distortions and then test on angular distortions?
Actually, we mainly train based on one data set, and I have train on one data set and test on another data set. But most of the data set both contains both these kinds of distortions. So I haven't tried to, for example, to test or train on compression and test on angular. I haven't tried.
That would be interesting to see if it detects only the distortion in training or if it's
suggestions. And actually here, I mentioned this paper has been accepted by ICIP, and ICIP only contains 5 papers, 4 or 5 papers. So here I don't show any data sets. Only one data set is shown.
We don't see your slides.
Oh, sorry. Yeah. Or here, I mentioned that I only use one data set to conduct experiments, but because this I reported this paper on ICIP and limited by the space limitation, so I only showed one data set on ICIP paper 2. But actually, I have done the experiment on other data sets, and this metric are consistent, perform better than the state of the art metrics. Yeah, I have done the experiments.
Any other question, maybe online for the remote participant?
I have a question. Can you hear me?
Go ahead, yes, please.
Yes. Did you consider using, instead of CNNs, depth separable convolution networks, like the one used in MobileNet, for example, to be able to have less computation and faster inference?
Here, actually, I have tried to use the some existing CM model like ResNet and MobileNet, something like that, to train them. But actually, this kind of metric, this kind of the network is too deep for the patch-based method, too deep. So you can see them. Actually, my model only contains several convolutional layers.
Yes, I see that, but I meant like instead of using convolutional layers, using depth separable convolutional layers. If you see what I'm trying to say, not like using a existing architecture, but use a depth separable convolution instead of a normal convolution, to be able to have less parameters maybe. And it's interesting to see if it will work as CNNs in this case. I was just wondering if you tested things like that or not.